Welcome everyone. Let's start the ABC-based seminar. Today's speaker is Justin Davey, as you know well, from the IISC. Today he will talk about the entanglement property of the gravitons. Please welcome him.
Thank you for having me here. The intro actually before COVID and now after COVID. I'm surprised that you guys take attendance for the for the meeting seminar. Maybe we should, because our attendance is very low. Okay, so I'll be talking about this work. It's done primarily with my student. Yeah, I have to get used to this. So, and it's based on his work. And let me start with the introduction. Yeah, so this entanglement is, of course, all of you know here that it's quite a difficult. Okay, entanglement is a difficult quantity to evaluate in quantity theory. All of us here know that. And evaluating it for gauge symmetry, theories of gauge symmetry, even if they are free, are quite difficult. As you will see, the subtleties involved in evaluating it. And the usual method of replicate fit has been successful in 2D CFTs. And it has, of course, as you know, it has played a very important role in holography and black hole physics. Now, and there has been, in spite of the fact that it has played a role in black hole physics, there's been little study of the entanglement entropy of gravitons by itself. So let me see, for instance, in the recent formula, this formula of generalized entropy, this object, this S bulk, this of course is the real Takanagi surface area, and this S bulk involves the entanglement between two regions in graviton, which involve particular gravitons. And such formulas, as you know, just a hint at the applications, as you know, played an important role in understanding the information paradox. Now, these motivations are sufficient to study the questions of entanglement entropy of gravitons, the theories of gravitons. And after all, it's a fundamental property. After U1, you would think that this is the next field you have to study. So let us go ahead and sort of look at its property. Now, the theory we are interested in is basically this, the linearized gravity. The nonlinear part is, of course, very difficult. First, let's just start with the quadratic theory. This is the quadratic theory of gravitons, and it admits this gauge symmetry. Now, the question we would like, the simplest question we would like is to ask is, what's the logarithmic coefficient of the entanglement entropy? So it's in 4 dimensions. There is a coefficient which grows like the log of the radius of the sphere. And, we are asking the question, what is that coefficient? It's quite a simple question. And the answer for free scalars is known, that's been calculated some time ago by Cassini and Huerta. And for Dirac fermions, it's known. Even for the spin 1, it's known, but I will sort of review that result. And can one, study just this coefficient? Can you just obtain this coefficient? That's the simplest question we ask. And the reason it's sort of a little subtle is the fact that this theory has gauge symmetry, and there is a Gauss law in the theory, and therefore the Hilbert space does not factorize into 2 tensor products. And in fact, I will explain this a little bit in detail. It factorizes as tensor products over superselection sectors, and there's a contribution because of that sum. And this is just words right now, but just to keep the picture in mind. But I will sort of detail this a little bit. So let's understand this idea. Why a theory with gauge symmetry has a problem or a difficulty. So we begin with the definition of the entanglement entropy. So what we do is we look at the constant time slice, and then we divide the region into A and A bar. And if the Hilbert space factorizes just as a tensor product, then you would trace out one of the regions, let's say the A complement, and then evaluate the von Neumann entropy of the rest, the reduced density matrix. So this is the formula that everybody is familiar with in this audience. And in dealing with spin systems, where degrees of freedom are just at a particular site, or like scalars or spinners, the Hilbert space does indeed factorize. But theories with gauge symmetries, including that of gravity, as we saw, the gravity has this nice gauge symmetry, it does not admit such factorization. And let's see it in detail. So I'll spend some time on the Maxwell theory. And we developed that, that study, though it was known for the 4-dimension case, we developed it slightly more in a more sophisticated way so that we can apply it for the gravity. So let's see this for the Maxwell theory.
So the free Maxwell and
free Maxwell
and the free free
free graviton is different. The coefficient is different, and what is the super selection sector? Yeah. So consider partitioning this thing, this Maxwell theory into A and A bar. Now, what are the gauging variant operators? It's useful to think about it in terms of the lattice first, just to get an idea. So what are the gauging variant operators? These are these Wilson loops. I mean, they go around the loop in a plaquette or whatever, in a lattice. And the degree, the way you formulate the theory is through the links, which are these U1 flux elements joining one side to another side. Now, if you look at the Wilson loop, maybe it's a picture. So if the Wilson loop is inside here, it doesn't change, for instance, the flux, this pink object which is coming out. I'm drawing this. Yeah. So pink object which is coming out here. And if the Wilson loop is outside here, it doesn't change the flux which is going inside. You can just imagine a spin system, and you can multiply its spin, and you would think that it spins localized on this this particular link does not change. So if you build up a Hilbert space, so if you want to build up a Hilbert space, you build it up by products of the Wilson loops or Wilson lines. Okay, and if it is lying inside, and if you think about the Hilbert space, given a flux configuration which is on the outside, it won't change that flux configuration. Similarly, if you build up the Hilbert space outside, outside Hilbert space, and you product over the links, it doesn't change the flux which is going inside. So if you think about it, the region, this flux, given a particular flux, you can build a full Hilbert space around it. So given a particular configuration of the flux, there is a Hilbert space. Now, the crucial thing after this is, so these vectors, of course, are labeled by, given this flux configuration, you can build a Hilbert space around it, because the inside operators don't change it. And so the subtle thing about this is that Gauss law connects the inside flux to the outside flux, right? So the Gauss law prevents this factorization, because the sectors are labeled by this electric flux, and together with the fact that the inside flux and the outside flux are linked by the Gauss law. So let's see that a little bit more explicitly. Yeah.
I understand Gauss law as this flux being related to the charge contained inside the surface.
Yeah. So I will show you how the application of this is a Gauss law constraint, which comes out by the quantization. So when you quantize the theory, we choose a gauge, say A not equal to 0 gauge, and then if you go through the path integral or any canonical quantization, you will get the constraint that the divergence of EI has to be 0 on any wave function or any gauge invariant state. Now, so if you take that condition and use a Gaussian pillbox around this particular region, around any particular region, you'll get the inside, the normal component outside is equal to the normal component inside. And that is just the consequence of the Gauss law constraint. So therefore, now what we have is that each Hilbert space is labeled by this electric flux outside, each sector. And together with the fact that the inside and the outside are linked by this fact, the Gauss law connects them. So therefore,
I'm still what do you mean by outside being linked with the inside? Because
so as I said, the Hilbert space outside is also built by by plaquettes here, by the you build it by the Wilson loop here. You build the Hilbert space by Wilson loop here. Now this, suppose you build a Hilbert space H outside by some products of the Wilson loop. Okay, on some vacuum, you build it up. But these products of the Wilson loop can never change the electric flux outside. I'm explaining again. So electric flux outside. So given a particular electric flux outside, you can have an entire Hilbert space. So, so there are various sectors labeled by this particular electric flux outside. Similarly, there are various sectors outside Hilbert space labeled by the electric flux, which are going this side. But the Gauss law links both of these guys. So that, therefore, it factorizes like this.
What do you mean by the Hilbert space out of products of Wilson loops?
Yeah. So, how do you think of a wave function? The wave function, for instance, wave functions can. I mean, this is a simple, a very abstract way of thinking about it, but it's a good way. I mean, at least for explaining this. So, wave functions can be thought of as product of monomials, for instance. Okay, on a particular identity or some vacuum or something. So first you define a vacuum. And then basically, you think in terms of the lattice, you multiply various, it's like creation operators, multiply various products. There's another way of formulating the gauge invariant Hilbert space. So you just multiply various Wilson loops. Just sort of functions, various functions of products. It's like, think of Wilson loops as A daggers, appropriate A daggers. In fact, as you will see, F mu nu, if you look at it, it will become, if you quantize it correctly, it can be written as A daggers. So if you look at this as products of A daggers, sort of, I don't know, how do you call it, polynomial or monomial of A daggers, and those are the various states you are allowed, then you cannot change these states. So, so a Hilbert space will have a particular flux configuration, and you can't link the two flux configurations. You can't change the flux Hilbert space, which has a given flux configuration, to another one. If you don't allow Wilson loops which are crossing this. So that's the
you would also have loops dressed to the boundary, right? So are they included in this? Like, I mean, are there only Wilson loops, or are there also Wilson lines like which connect from the boundary?
Wilson loops are invariant. Yeah, Wilson loops are invariant. Yeah. So so that's what the argument is, that somehow the Hilbert space factorizes, but it factorizes in this particular manner in which the electric flux inside and outside are linked. Okay. So consider, now let's consider that. Consider a particular sector. Consider a particular sector. So there is some psi wave out and psi in, and then you trace out the psi out. Okay. So in a particular sector, you can reduce the density. You can define a reduced density matrix. But the Hilbert space is actually a sum over the sectors. Okay. And therefore, the density matrix is actually, density matrix of this kind. So it's a sum over the various sectors. And this is the probability Oh, I'm to the inside this. Sorry. Last time also I gave it. Yeah. So there's a probability that the system is in that particular one, in that Hilbert space, in that super selected Hilbert space. So people call this super selection sectors. So there is a particular electric field configuration, and this is the sort of density matrix in that particular configuration. Now let's perform a partial trace in this. So we trace out this row out, and then therefore the reduced density matrix is basically the sum of the reduced density matrix with the PE. I'll define PE slightly more carefully later, but roughly speaking, I mean, you can imagine the density matrix factorized like this with a particular, given a probability, given a configuration electric field, this is PE and so on.
So can the ridge line cross the boundary and somehow inside the boundary?
Yeah, so that's not allowed because that that is not a local gauge invariant operator from this inside point of view. So that's the problem, and that's the reason there are no local observables in this sense. Like when you define a particular region, you can talk about local observables inside and local observables outside, but you can't talk about things that are crossing, and that's the reason it's happening. So it sort of factorizes like this. And then if you go, you just take this formula. every time
I asked another one.
I sort of, I'm used to the other pointer. That's the reason. Last time I think also I came in there. Yeah. So, we take the partial trace, and then you just substitute in the von Neumann formula. You get this thing. So you get two terms. This term is just because of the fact that there is essentially that term comes from taking the log of this, and there is this log of pi. It comes essentially from that, and that term has this which I call in green. Actually, that sort of is what we call the edge means. And then there is the regular term. So there is a decomposition of this into two parts. Just because one is just because of the fact that a super selection sectors, and one is the usual kind of bulk mode, as they call it. Okay. So then what we need to do, in fact, what we will do is we'll review this, because to address the graviton, we have to address similar features. So what we will review this, though the U1 has been calculated. I will give the references later. The U1 theory has been calculated, but we'll refine that calculation and make it in such a way that we can generalize it to the gravitons. And in fact, the way we do it is it is suitable to do it in arbitrary dimensions, as you'll see, and it's very convenient to the way the formula comes out. And there is a check also. There's a sort of observations we'll make, that the contribution, that P log P, the green contribution, is actually can be shown to be something called the edge Harish-Chandra character for the U1 field on arbitrary D. And this is actually gives us a check for the graviton, because we see this in the U1 that it is something like the edge Harish. I will define all this edge Harish-Chandra character, and then what we will see is that we will see our calculation for the graviton is also having this property. Okay, so then of course what we'll do is we'll repeat the same thing for the graviton, and then we will sort of see the agreement. So let me go ahead with the U1 theory. I hope the sort of rough plan is clear. I have 1 hour, right? Okay. So the U1 theory, and what we are interested in calculating this. Okay, and we are imagining that there is a particular electric field configuration, and we want to compute PE log P. What is PE? Okay, so that's the first thing. So the U1 theory is free. So whatever the distribution should be a Gaussian. It should be a Gaussian, and whose standard deviation has to be the 2-point function of the radial electric. So this is a given electric field configuration, and we are interested in what is PE. So since it's Gaussian, we are saying that it should be just 2-point function of the radial electric field. So we write a formula of this kind. So you can see the 2-point function. The Gaussian is controlled by the standard deviation of the 2-point function of the radial component of the electric field. 0R is the electric field, and then it's a normalization. And then we compute P log P and sum over the electric field. And if you go through that calculation, essentially this normalization is what gives you the log term. You have to sort of go through it and see. The normalization is what gives you the log term. Essentially that turns out to be a log of the determinant of that 2-point function. So the calculation has been reduced to calculating the log of the determinant of this 2-point function. So the strategy is straightforward. We quantize the U1 theory and then evaluate this particular correlator and obtain its determinant and extract the log term from there. Now, so the quantization, because it's spherically symmetric, it's convenient to do it in spherical harmonics. Okay. So we take the U1 theory, we expand the vector potential in terms of its harmonics. So you can see there are two classes of harmonics. You can see that this is a scalar, a harmonic, and here is also a scalar. Actually, you'll see that because it does not have theta and phi directions, so it's a scalar. And here is the true vector harmonics. Okay. And here, this is a scalar harmonic, and YR is also a scalar harmonic. And then there is the vector harmonics, which can be written as the derivative So that's the expansion of the electric field. And it's good to define these. T hat is in the time direction. R hat is in the radial direction. And these are the two angular directions, E hat and M, which are defined by the directions of the harmonics themselves. And this is just projections and so on. Just if it is E, it is in the direction of E. If it's M and so on. So we choose a gauge. It's okay. I think I've got used to it. I think I got used. Yeah, we choose a gauge that the E is 0. The reason is that because if you see this, if you see the expansion of along the tangent direction, this is gradient. It's the gradient of the scalar. So you know that the electric field, the gauge transformation is gradient of a scalar. So therefore, by gauge transformation, you can fix this component to 0. And essentially, after eliminating a naught due to the constraint, you're left with 2. Just because it's helicity 2, you can imagine that it sort of reduces. So you're left to do 2 degrees of freedom, the AR and the AM. This is the other directions, and its conjugate momentum. And then you can find its equations of motion. Basically, we are quantizing the Maxwell theory in spherical harmonics. Usually, you do it in plane waves, but here it's in spherical harmonics because that's the geometry which you're interested in. So there's this wave equation, it obeys, and you can expand it in modes. I mean, though you don't see it very much, all the details very much, you can just understand that what we have done is we have taken the 2 degrees of freedom after we fixed the gauge and expanded it in such a way that it's consistent with spherical symmetry. And when you do that expansion, you see it's similar to the plane wave expansion, except that e to the ikx is the Bessel function, just like what you get when you do spherical quantization. So that's the expansion, and of course they have the canonical commutation relation and so on.
This is S4 calculation?
No, this is because you have time and you have the sphere. You have time and
T cross R
is like S2 because it's a sphere and the radial direction on the sphere and the theta and phi and then the time and the time. Yeah. So it's that quantization. I mean, let me have a picture for that sphere. So you have time and then a sphere at a particular R. R is that spherical surface. And therefore, we're doing quantization and the radial way. And what you're interested in is basically the F0R theta phi correlator. This is the electric field correlator. Yeah, so that's the picture to have in mind. So because we have expanded, we have expanded these the Gaussian fields. We can actually compute these things now and compute this 2-point function. These A's and A daggers actually obey the same commutation relations. They obey the same A pi, and because of this canonical commutation relations, these obey the same. So we have canonically quantized this. I think this might have been known in some literature, but one can redo it quite simply. So we can easily quantize it and then find the electric field operator. So this is TR, that is the 0R, and it's related to the pi, one of the field which we expanded it. And therefore, we can just plug it inside and find its correlator because this has the expansion in terms of AA dagger. And then you plug this guy inside here, so AA dagger and commutation relations. And when you do that, you get a following integral of this kind. This is around the vacuum. So finally, it will be a number. So you'll get this particular thing. Note that the L and the L plus one somehow comes here. And so this is the particular thing. And this is dk. And this integral is known, actually. This integral is known. And when you do this integral, it's some Legendre function of the second kind. It's related to some hypergeometric, but it's known. I'll tell one property which we need, that's all, from this, right? So right now we have put r prime, theta, theta prime. So we're just finding the 2-point function of the electric field at 2 points, but it's done in spherical coordinates. That's all. But we have to put it in the same sphere. Okay. So this is known, and maybe it was known in the literature some time ago, but it's simple actually. It's just convenient for this problem to do it this way. Therefore, and if you see the structure of it, because it's YLM times YLM, in terms of YLM, in terms of LM basis, it's very easy. So this is in position basis. If you write like this, it's in position basis. Here, it's in angular momentum basis, and therefore, in that basis, it's just diagonal. It's just diagonal. So the operator is diagonal in that basis, and all we need is this in the same r is equal to r prime limit. And what we can show from QL, from that second kind, the jump function of the second kind, when r is equal to r prime, it is actually independent of L. So that's a constant, independent of L. And then then we have this diagonal L into L plus 1 by this. So therefore, the eigenvalue, this operator, which we want to find the determinant of, is proportional to the eigenvalues of the Laplacian of a scalar on S2. And that is known, of course, that's known, the determinant of a scalar on S2. So that's the end product of this, the edge mode. So let me just sort of run through it with it. So we are computing P of PE, sum over the electric field configuration. It somehow is related to half determinant. After going through the formula determinant of this operator, and this operator, in this YLM basis, it's just diagonal and it's proportional to the Laplacian. This is the crucial term.
So I can understand now you choose regulation. You use the regulation choice for the entanglement side.
I use this.
The regulation choice. Because now in the S2, you only have a regulation field. So I think it's conform to the Cassini regulation choice.
I don't understand. Sorry.
In the Cassini's paper, they said that the way
Cassini.
Cassini paper, they said that entanglement side definition is not ambiguity. And then they say they have regulation choice, negative choice, or trigger choice. So because now I think that in the S2 case, you only have a regulation field.
Yeah.
So I think it's conform.
Yeah, it's an electric choice. Yeah, it's electric. No, I understand. Yeah, it's the electric choice. Okay. Yeah. So then we find this determinant. As I said, it's a determinant, and we just have to find the log of this guy. And there are lots of methods to find determinant of a scalar. There's a lot of methods to find sheet kernel methods and so on. But we will look at a particular method which has a little bit more structure. And here's the thing. It's actually due to recent work by Aninos and company. And DNF and all. So you can write this determinant after a set of identities. It's just trivial transformations of certain identities. Essentially, writing this log by its integral representation, right? And you do a lot of manipulations, and you can write it in this following fashion, actually. It's due to Aninos, very recent. You can write it as a transform. This black part, this red part is a transform. I'll say why only that part is a transform, as you will see later. So it's a transform of something which I call a character right now. Okay. Right now, this is due to some identities. That sum has become an integral of this kind, and there is there's a character associated with it. And to find the log term, all you have to look at is the 1 by t coefficient. You expand it in t, and you expand find the 1 by t coefficient, and so it turns out.
This is the type of chi is same as the kernel in that integral, or what?
Yeah, no, it's the same. In this particular case, it is the same. It's not a type. I'll give you the general formula soon. Yeah, it's not a type in this case. Yeah, it is the same. Yeah, so you just find find this coefficient, and yeah.
Actually, I missed how the contribution of entanglement entropy is given by that log determinant.
So let me just give.
Yeah, I thought that first it's just free energy is on sphere.
Yeah. Finally, it is a free energy on the sphere.
Yeah.
But initially, let me go back. Since it's a very informal thing, I can just go back. Yeah. So what we have to do is this is the probability, and we have to find in PE this is the probability error. So roughly speaking, P is equal to some normalization. That's the crucial thing. Minus half E G R inverse. Like this. So what we have to do is compute log P and sum over E. We have to do this. So it's log n, right? Because I take log of n minus half E G inverse E and multiply by, because P n e to the power of minus half G inverse E. Or this is P, right? So if you look at this, okay, if you look at this, this is log n, which is a number, and this is just the PE, and sum over E. So this is normalized to 1. So we need to understand what log n. That's the first term. But this term is actually like a volume. You can see that this is, roughly speaking, n, expectation value of E G inverse E in this. And this actually, okay, it's a calculation actually. You have to show that, and this is roughly a delta function because there is a G inverse, there is E G inverse. So there is G inverse and E is actually G. So it's G inverse G. And this is the, if you correlate between half of G inverse. So this is the 2-point function, G inverse times 2-point function of G. So which is G inverse times G. And this turns out to be a delta function which goes like a volume. So the log is here, and the log n. The log is here. Yeah, it's a detailed calculation. The log is here. And the log n is basically, the normalization of this, which is the determinant of GR. So that's how. So the steps involved is that you have to compute this and identify that the log n contains the logarithmic term. Because we are interested only in the log R by epsilon. And this actually goes like volume. That this is detailed calculation. The rest of the term goes like volume. And this contains this. And if you look at this, n is just the determinant because that's the normalization. So that's how it comes. Yeah, it's a little.
Are we doing a Euclidean calculation or?
No, it's Lorentzian calculation because time slice is chosen and you're quantizing it.
How did you reach this is the probability of the H mod? Did you explain that or maybe I missed it?
Yeah, because I said that it is free theory. It's a free theory, and 2-point functions are dictated by correlators in that free theory.
Okay, you didn't show how it reduces the 2-point function. That's correct, right?
Well, for instance, here, if you take 2-point functions, GRR, if you take the 2-point function correlator here, that is dictated by this.
That's right, but like how the entanglement of the calculation reduces to this 2 was not shown, right? Or did you?
No, okay, I don't know. Let me go back. So I said that the entanglement entropy has 2 parts. Okay.
Yeah, this H part
and this part, and this is what I'm computing now.
But and that just reduces to this 2 point.
Yeah, so that reduces to this Gaussian. So we make PE is like a Gaussian because it's a free theory, and then we take we just calculate that. We just look at PE log PE and just calculate it. Yeah.
So just to clarify, you think of the H mod as part of the interior of the subregions degrees of freedom.
Well, so again, okay.
I could have thought
since it's informal. Yeah. So the question is whether you want to include that or not. Yeah. That is the question you're asking. Yeah. If you go through this calculation, just write this out and go through it. It's included. But there are various prescriptions. Some people, in fact, truly speaking, people don't like to include that.
90 to see the H mod, you have to go outside the region.
Yeah. So you don't, people don't like to include that because in the sense that they say that that is like, that is not in a pure state because it's a sum over the superselection. So that's why people don't include. There are prescriptions in which you don't have to. There are very complicated prescriptions in which you don't have to include. I will tell you, when you combine it, there is a nice property.
Yeah. This low coefficient, right? Like, why is it like interesting? Like,
Yeah, so log coefficient is the invariant one. I mean, the area thing is not invariant. It's not invariant. I mean, it changes under renormalization prescription. Log one doesn't actually. Yeah.
Log one doesn't change under renormalization.
Yeah. Because if you scale it,
The coefficient.
the coefficient. Yeah.
And just to continue this previous comment, like if you chose the magnetic prescription, would this log term be same
No,
or?
this particularly, we have done the magnetic one also. It doesn't change. It's the same number.
In 4D, you would expect that
Yeah.
because there's a duality and so on, but like.
Yeah, higher one I haven't done. Yeah, we haven't done, but there is a formalism is there to do it. Yeah.
I read this paper before. If you have a EM duality, you can always show like that's your choice, and you may choose uncreepy.
In 4D.
I said if you have a duality,
Right.
you can have
Then it's the same.
P-form symmetry in some dimensions, but we can have a electromagnetic duality. So you can always show equivalence between electric and magnetic choice.
I haven't done very much. I don't think I've done anything so far. Let's see how much we get. Okay. So we expanded, and I think we have reached the stage in which it was shown to be the Laplacian, and then there is this particular nice property that we can write the determinant in this manner and expand. Now, this method is not our method. In fact, it has been done by Soni and Trivedi earlier, but they had worked in Cartesian, actually. And then, they worked in Cartesian, fixed the gauge, in Cartesian, and then converted finally into polar coordinates and performed the spherical decomposition. Right. So the only thing we have done is we started out with the spherical wave and did the quantization. And what's we compared it with their results. And in fact, their results for the 2-point function for two different theta and theta prime is the following answer. You can go and look at the paper and say answer. It's sort of a sum like this, right? With the product of the y lengths there as PL cos theta. Addition formula relation, and it's a relation. It is what they have in their paper, and they had to do some work to extract the log term from here. But this is what we got. They got, and we got that that nice Legendre function of the second kind, and you can just compare it by this alpha expansion, and they do agree. We haven't shown identically they're the same, but we did the expansion, and we saw that they are the same. Now, with this formalism of doing it in spherical way, we can do it in arbitrary dimensions. And okay, so this is the kind of summary of it. And S bulk has been computed actually by various authors, including us earlier on also, by various methods, and that is 16 by 45. And if you combine them as somebody else, so yeah, without by Cassini, Huerta did, and some Huang has done it earlier. We did it also. We did it for a particular reason, but we have confirmed that. And if you combine them, the combined version is actually the Euler anomaly. So separately, they are not. If you combine these two, it's the Euler anomaly. And in fact, ADS-CFT actually sees the combined version somehow. But in the information theory, actually, as you said, so you would not like to have the edge part, actually. Yeah, but this is what is the status in the sense that ADS-CFT somehow sees what A. I don't know the combined thing, which is the anomaly. I don't know the reason yet. I don't know whether people have studied. But so, in fact, this approach allows us to generalize this to arbitrary dimensions very easily, actually. Because all you have to do is generalize the spherical harmonics in arbitrary dimensions.
So is that this AD-CFT statement, is that a statement about the boundary conditions? Are you are you working with the chemical potential fixed, or are you working with the charge density electric? Is that the issue?
Yeah, so it's by using the Ryu-Takanagi formula. I don't think it's been investigated so much. So you take the Ryu-Takanagi formula and just look for the coefficient of the epsilon, log epsilon term.
How does it change with the boundary conditions in the bulk? Are you fixing the?
So I think they sort of
normalizable, non-normalizable kind of. That's what I was
I don't know.
asking.
Ryu-Takayanagi formula is just the evaluation of. I don't know whether people have studied it in so detail. Ryu-Takayanagi formula is just the evaluation of that minimal surface, right?
But including the back reaction of including the bulk, I mean, it's generalized formula, right? So
no, I think this is the classical one they have done. They have not used the generalized formula here. It's just the classical one. You just take the classical one and just evaluate the usual Ryu-Takayanagi formula and just evaluate it. It gives the A-type anomaly.
When you say anomaly, it's both this H mode and the bulk.
Yeah.
Together, it's
Yeah, somehow together it's anomaly coefficient. Yeah, and there is general arguments also by, somehow when we have general arguments using the replica trick, for the log term, the general arguments give the anomaly coefficient. I mean, there are general, like, a replica trick is like a cone and then a deformation of the cone. Then, it's a stress tensor which comes in when you think about it in that language. And then you get the anomaly coefficient.
One more question. Yeah. If I consider 2 plus 1 dimension and I'm considering abelian very simple Chern-Simons theory, then if I repeat this calculation, then I will have only the boundary contribution term. There is no bulk term.
Yeah, that's what in the morning we were discussing. Whether it is just that. I mean, that separation is not known. The full answer is known. The full answer in Chern-Simons theory is because it is odd dimension. It's odd dimension, so there is no log term, but there's a finite term. And if you want Chern-Simons theory at level k, the answer is for the spherical it's log k. The k is the level of the Chern-Simons. Now this is done using this Cassini-Huerta map and so on. I mean, where you map it using the conformal symmetry to a sphere and evaluate the partition function of sphere. But the split, I think, as far as I know, just discussing in the morning, is sort of not wrong. But most likely, what you're saying is the intuition is because there is no bulk degrees of freedom, you would think that everything is log. Yeah, I understand. Yeah. So it can be generalized to in d dimensions very simply, and you can already see the structure. So this is the Laplacian of d minus 2 sphere. Okay, because 4 dimensions, 2 sphere, d minus 2 sphere, and you can evaluate the edge mode, and it becomes the determinant of that Laplacian. And then if you evaluate the determinant, it is this form again. The structure comes out. So here it's a transform of this particular thing, a character of this kind. Now you can rewrite it. You can use the Aninov method and rewrite this determinant in this manner. And you can get the transform of this particular scalar, character. And this character is something called the Harishchandra character for a scalar, actually. Let me just roughly say what that means. So you just consider a minimal coupled scalar in d minus 2 in the de Sitter space, because de Sitter space is connected to the sphere, because the continuation of that is actually the Euclidean version of that sphere, is a sphere. And you consider the de Sitter space and define this particular dimension. It's almost like the ADS CFT mass dimension relation, but with a minus sign because of the de Sitter, minus sign in that. And you evaluate this thing. Just trace over the representation for a given delta plus and delta minus. And you get this particular form. You get this particular formula. And in fact, this is similar to, just to get the idea of the Harishchandra character, I've done it for the SU2. SU2, you take the J3, and then you take the trace over the representation to get some structure like that. So it's something like that. It's a character of that kind. And if you evaluate it for the massless scalar, it is indeed this. So therefore, it's a transform of the Harishchandra character. The determinants are transforms of the Harishchandra. It's a very recent observation, I think, first by Aninov. We just generalized it to the P forms, arbitrary P forms, but the observation was by Aninov and all.
So is it just e bar IT times the kata of the group?
Yeah, it's a kata. So delta plus is the kata of these scalar, these representations. And you take over, trace over all just like the SU2. So, so for the massless scalar, this is the Harishchandra character. So what happened is that we saw that we saw that the edge mode can be written as the Harishchandra character of a sphere of the massless scalar in d-2 dimension. And now let us look at the partition function of the full U1 theory on SD. So this is a little bit different now. We're just looking at the partition function of the U1 theory on SD. So that means S4. Now again, by Aninos and all, it actually splits this full partition function of vector. Now we are looking at the vector, the full vector. It splits into two parts, the chi bulk and the chi edge. Okay, chi bulk has a particular representation for the character, and the chi edge turns out to be exactly that edge mode partition function. So you take the U1 theory on SD, just write it. It's determined in terms of this, this decomposition which Aninos, Denef, Aninos and all found. And then from there, you can extract the edge mode trivially. I mean, the reason you can extract it is because this denominator, you see, the denominator is lower, d-3. Okay, it's lower dimensions. Okay. So from there, you can extract the edge modes. So there is a very simple prescription to extract the edge modes from the Denef, Denef et al. Formula. You write the using their methods. You write it in terms of the Harishchandra characters, transformation of Harishchandra, and then there is a natural edge part. So there is these complicated methods is a very direct method of calculating, but using theirs it's very simple for the U1 theory at least. Now the question is whether such pattern holds for graviton. And in fact, that's a check for us, the way we do it. So the gravitons. So I hope the structure is clear. We did an explicit calculation, and then we saw that it was the edge mode, some kind of determinant of the scalar, and that is the edge mode of the partition function of U1 theory on the full scale. Now let's look at the gravitons. Again, this is the Lagrangian.
So here I have my question. So when you define these RT surfaces, they are generally on some background, fixed background.
Yeah.
But here your metric itself is fluctuating. So how do you define that external surface?
No, there's no holography here. This is a direct calculation. There's no holography here. It's just field theory calculation.
Okay.
I'm saying that if we want to get entanglement entropy using holography, then it always comes as a anomaly coefficient. Here we're just doing a field theory calculation. So we consider the linearized gravitons, and this is the gauge invariant object, right? Like there, the field strength was the gauge invariant object. Here, the Riemann tensor, the linearized Riemann tensor is the gauge invariant object. Einstein's equation is this. And in case of Maxwell's law, the Gauss law resulted in the superselection sectors. So we need to obtain a gauge invariant characterization of the superselection sectors. Okay. And so here the U1 theory, in this case, the Riemann curvature is the field strength. And that should be the analog of the U1, the gauge invariant field strength. So somehow we have to cast this Riemann tensor in terms of similar to U1, and then we will sort of get an idea. So, so let's define this U1 potential. I think it's known in gravity literature, but I have not seen it explicitly elsewhere. It's sort of a combination of the Christoffel connection, linearized Christoffel connection. So you define this U1 kind of putative U1 field, just derivatives of the linearized metric. And then if you look at the gauge transformation, so here the gauge transformation is this, and you look at the gauge transformation, right? You look at the gauge transformation, it moves exactly like the U1, where the gauge parameter is this. So this combination transforms like the U1, okay, but with alpha beta index. So and the Riemann curvature is exactly the field strength of F mu nu alpha of this A. So you can cast the Riemann curvature as field strength of this putative U1 field, and the transformation property of this A is exactly like that of U1. So using this, it's reasonably easy to find the what is the Gauss law constraint in terms of gauge invariant variables. So the Hamiltonian constraints are these. Right, for the gravity, and using the Bianchi identities, actually there is some manipulation. You can transform this to imply this constraints imply this. So now we have cast the Gauss law constraints in terms of something almost similar to the Gauss law. You see, this is the del mu of R mu J, and that's also something of that kind.
A is not same as a spin connection, right?
No, it's not the same. Yeah, it's just bilinear. You see, it depends on H mu. So it's not H mu is a bilinear of the spin connection. Let me go back and show you. It's actually
again linearized.
It's linearized, yeah. So in fact, I don't know. I mean, it's basically, I think, a rough. You bring the Christoffel symbols down, and then you like all of them down, and then you look at this antisymmetry. A is that. So you bring the Christoffel symbols down completely, and then you antisymmetrize these. These are symmetrical. You antisymmetrize mu nu. So that is this, because it's antisymmetric in alpha beta. So yeah, so you see that Gauss law constraints. Gauss law constraints actually become simple. We can cast this in terms of curvature itself, which is gauge invariant, and then then look at its. So therefore, I mean, from our previous experience, these fields transform almost like U1. So all we have to do is find the 2-point functions of these things. So this curvature component is analogous to the U1 field strength, and the constraints are obtained from Hamiltonian constraints, and these are the Gauss law constraints here. And so the super selection sectors are labeled by these, basically, these electric fields. In the language of this, these are the electric fields. So there are 6 of them actually.
Future we need to label the components by the center. How do I understand these components are center? These variables are center.
From the lattice point of view, yeah, that I don't have an understanding actually. From the like the way the U1 is, I'm using this fact that these fields, these curvatures are consistent, constructed by an analog of the U1 potential. Right, this is a potential, and it transforms exactly like a U1. Yes, with the alpha beta index. And the curvature is the field strength.
I agree, but it's not even for U1 case, I remember some level we will use the electric field because this electric field is a center. So now we just do the analog.
But
but you also need to check the computation version.
Yeah, we haven't actually. So the check we have is basically the edge mode check.
Yeah,
the check with the edge mode partition. Yeah, we don't have like the first principle construction like within the lattice, then you can, we don't have that because I don't know how to do this on lattice.
Of course.
Yeah.
Okay.
Yeah. So. So we have 6 components.
You don't know how to do spin 2 fields on lattice.
Well, maybe there are, but I haven't studied them. Maybe there is some formulation.
I think the difficult is that you work rapidly for
Yeah, that's true. So there are 6 components. You can count 3 of them there. These are spatial, and then there are that is antisymmetric. So there are 6 components. The strategy is, of course, we gauge fix, quantize the theory in terms of tensor harmonics now, and determine. We also had to determine these field strength in terms of the the variables which we use to quantize, the pi and the a. I mean the ones which have the commutation relations. So in fact, and we need a local relation between that. So we look at the local relations. If you remember the electric field, maybe I flashed through quickly. The electric field was locally related to the the pi's and so on, the variables we are using to quantize it. So so we sort of go ahead with the quantization in tensor harmonics, so there is some formalism to do it. So again, we break it up into some tensor modes, vector modes. So these are. Tensor mode is when both indices are spatial. Vector mode is one is in the time direction and one is in spatial. And then there is a scalar mode in both temporal. So there's 1 scalars, 3 vectors, and 6 tensors. And it's a decomposition. And then what is important again is that we can fix everything. I think this kind of quantization was first done again by Benedetti and Cassini. So when you fix the gauge, you can set all the, everything sort of, you can either set to 0 or related, and only 2 of them, just like the fact that there's only helicity too, only 2 of them are actually invariant, and there are 2 of them, and it's conjugate relations. And then you can find the equations of motion and try to quantize them. So there's the equations of motion and quantize them. And again, there is a very similar structure for its wave function expansion in terms of Bessel functions. Very similar, these coefficients slightly different. So we have the canonical variables, and we have expanded them, and they have this commutation relations. Now it's just a matter of using this to find the 2-point function. But there are 6 components which we have to look at. There in the one field there was only 1, the radial electric field. Here there seems to be 6. But if you expand these in terms of, if you expand all the curvatures in terms of its spherical harmonics, you see that only 2 of them are locally related. And these things have radial dependence, so they're not local inside a particular region. So we don't look at these, we look at the green ones. There are 6 of them. We have evaluated all of them, and we have shown the other ones are non-local. So we, out of the, there are only 2 of them which are local. And we go ahead and, so these are the 2 of them. And we go ahead and sort of evaluate its 2-point function. The same strategy. And again, we wind up with that Bessel function of the second kind. I mean, the Legendre function of the second kind, but different coefficients. So that's the crucial thing, different coefficients. And both of them, both of the modes which are locally related have the same determinant. And we have this particular formula for the determinant. And if you evaluate the log coefficient, it's some -16/3. Okay. So what is it? I mean, how can you say anything is right? I mean, it's a lot of calculations, and it's some 16/3 answer. Now, let us look at the partition function of spin-2 field on S4. And using the Aninos-Denef method, it splits into 2 parts, the bulk and the edge. Okay. And they have in their paper, they have given this actually, this expressions, the bulk and the edge. And the edge was this. If you extract the log coefficient from the edge, it exactly coincides with the 16/3 actually. It agrees with this complicated method, the direct method of computing. The bulk contribution, which I didn't talk about in this talk, and which I didn't even mention in the seminar, has been calculated. There are 2 ways of doing it: the hyperbolic cylinder and this, and that's 1661/45. It has been computed, and together it is some number. But unfortunately, here in this case, because this is spin-2, and there is no sort of trace anomaly for spin-2, and therefore, like this coefficient, I mean, you don't have an understanding. The total coefficient, you don't have an understanding whether it is something related to spin. So in fact, because of the connections with partition function, you can generalize to arbitrary spin. And here is the answer for arbitrary spin, actually. It's reasonably simple to generalize it. But this direct calculation to check this is the edge mode is pretty hard to do, actually.
So what is evidence?
No, yeah, right now, in fact, it is just, I used just the partition functions and just written it down. There's no check. Other than for s = 2 and s = 1.
Okay.
Yeah. Yeah. There's no check. So that sort of concludes this, and I can stop.
Can I just confirm?
Yeah.
You were saying if you have some higher spin field, you should be able to reproduce this from
the direct calculation which I did. For instance, if you have a higher spin field and you could do this quantization, in fact, it's reasonably straightforward to extend it. You could do this quantization and calculate the 2-point function and evaluate its determinant. Cronstall 3. Yeah, 3. Could be possible. I mean, it's
how did you get the formula again? You had the 1 and 2 case, spin 1 and 2 case, and then
because this S bar. So, for instance, this. Let me see. Oh, I'm going forward. Okay, again, I get confused. These things are known. These things are known. This whole thing, this partition function is known for arbitrary space by Denef et al. So from there, you can get the edge. From there, you can get the edge. So you can generalize this to arbitrary case like that. And if you want to get the bulk, in fact, Cassini, they have made a conjecture for the bulk. This formula, yeah, this is their conjecture actually.
No people calculated the space entanglement.
Who? No, I don't think so. Directly, no.
Okay.
Yeah.
I don't have, but some
Yeah.
expressions that.
Yeah, maybe they have. I don't know. But yeah, so, yeah, but this is a conjecture due to Cassini.
You also have the
We have this from hyperbolic partition.
you also have the magnetic version of the spin 2 calculation.
Magnetic version. Yeah, I don't. Well, yeah, some other center, basically, some other. No, we didn't do that. Yeah, we did only the electric centers. Yeah, yeah, we didn't do that fixing. But the thing is that we looked at our quantization because these things depend. I mean, we have a scheme of quantization, and the local variables are only these two, and we took the local variables, all the local variables in our quantization. If you look at backwards. So if you look at all the curvature, from the Gauss law. So if you, so you'll have to look at some magnetic version of the Gauss law in this particular case. Yeah, we haven't done that actually. Yeah, some magnetic version of the Gauss law and to check. Yeah, whether I think for vacuum electromagnetic duality, some duality exists for spin 2.
Even I didn't know. Okay.
Yeah, I think it's there.
In
Recent
4D.
papers,
In 4D, you mean?
4D, yeah, in 4D. Yeah. Recent papers by Cassini. I think they have some paper called Generalized Symmetries of the Graviton. I think in that paper. Yeah. So, okay. So that's it. So I can actually stop here, or if you give me some 10 minutes or something, I can tell you one more property of the entanglement of graviton. It depends on you guys. I mean, I can stop here or 10 minutes. 10 minutes. Okay. Yeah. So we have studied, of course, the vacuum and what about excited states. And one of the simplest things which a lot of people study is like you create an excitation and you study its evolution and see how entanglement jumps. This is sort of the easiest we could think of to do, actually. And study the time dependence. So the excitation, we create the density matrices of this kind. So essentially, there's an operator inserted at some position, and we evolve it in Minkowski time as well as some Euclidean time. I'll tell you the reason for this Euclidean time. And you evolve it, and this is the density matrix you're looking at. So it's no longer the vacuum. It's this vacuum with this excitation, and evolved with this. There's some normalization. And this imaginary part is basically it gives a width to the excitation. I'll show you how it gives the width to the excitation. And then you evolve it. And so let me have a picture for this. So it's easy. When you have a picture. So let's look at this. So this is your half surface. The surface is in the XZ direction. And this is the Y direction. We are creating an excitation here, right? And it, as you will see, this is the picture you have in mind. The excitation actually travels like a spherical wave. And this is the entangling surface. This is sort of the next easiest thing to do, actually. Though the setup looks complicated. So entangling surface, and this pulse goes into. And then, of course, if you trace out this, the entanglement entropy will jump. And the question is, how does it behave with time? So here it is. So yeah, that's what I've been saying. We create the excitation, and because of the time dependence of that density matrix, it evolves. It gets into this region, and we trace out the half region. And this is a co-dimension 2 surface, and we will see that things can be organized according to the symmetry. So actually, this phi and F minimum has been studied earlier, but this organization things, I think they haven't noticed. I think by Japanese groups, and phi and F minimum has been studied earlier. And we, of course, generalize it. These are the invariant operators you can insert. So we have to insert a curvature and study its excitation. Now, just to understand the nature of these excitations, I said this is a pulse and it moves into this. But how can you see that? For S equals 0 and 1, you can insert a stress tensor and evaluate its expectation value in that density matrix. But for the curvature, you can't do that. There's no local stress tensor. So we actually insert a Kreshman scalar. And when we insert a Kreshman scalar, this is the formula. And you can plot this, it's a formula, but you can plot it. I didn't have time, so I just took it up on the paper. So at t is equal to 0, the pulse is at, it's a spherical pulse. The pulse is centered at t, centered at the origin. Then it sort of expands, and you can see at 2 different times. I've given the width, epsilon is some width, and you can see it at 2 different times. It sort of decreases the width. In 2 dimensions, it doesn't decrease, amplitude doesn't decrease, but in 3 dimensions, higher dimensions, because the flux, the energy is constant. So the amplitude decreases and it goes into, so you can see from this construction, it's actually a spherical pulse. And we evaluate this entanglement entropy here by tracing out this particular, and the calculations involve, it's a little complex calculation, but it involves a 2-point function on the cone using the replica trick. And you can, there's a simplification when you take this width 0 limit. And what we show is that this entanglement entropy, the time-dependent part, the Rene entropy, in fact, is nth powers of the polynomials. The polynomial is the distance y0 in terms of the only scale in the problem, y0 and the ratio. This ratio determines the time dependence. And we actually evaluate all these polynomials for all the components. And here is this, for simple example, this is very nice property. Like the scalar is just very simple, 2f plus 1 order polynomial. This has this order polynomial and so on. And these polynomials are tightly constrained actually by certain properties. Now here are some plots actually. Everything saturated log 2 because it's like there is somehow understanding of this as 3 entangled pairs. So it saturates at log 2, and there are various ways it saturates. And the time dependence is entirely sort of known. Okay, there's another one. So maybe I will end. So I hope it is anything that is reasonably interesting. Even such simple questions are not understood for the graviton. And after all, it's sort of the field which occurs in nature, and it's good to study that. And it's this edge modes, whether it plays a crucial role in this particular formula is sort of good to see. There are some setups where you can test it actually, the growth of entanglement are controlled by these polynomials. It's constant under these symmetries. Okay.
Let me ask one question. So, is this you talk about this anomaly? Is it anything to do with this? You also mentioned this edge mode, right? And edge mode people work with this anomaly flow and anomaly matching.
Right. Okay.
So here, this anomaly, nothing to do with that anomaly.
I don't know. Here in 4 dimensions, it's the Euler. So in the trace anomaly, has 2 coefficients. It's A, and it comes with the Euler density. And the B, which comes with the W square. Y tensor square. Right. It's only this coefficient. There are 2 coefficients in 4 dimensions. It's only this coefficient which controls the log term, according to general arguments in ADS-CFT. And replica trick. You use the replica trick, somehow you get the full coefficient. But if you just explicitly calculate like the way Cassini and all calculate, by just quantizing it, you get this separation. You get this two separation. One is the edge mode contribution, and one is this the whole thing, and together they become the graviton case is like there is nothing like a stress tensor because the graviton doesn't have to have a local stress tensor. So this kind of checks. We don't know what that coefficient is actually.
Slide question. So you mentioned that the edge mode can press on rows in the generalized integral formula.
Yeah.
I expect the edge mode just correspond to the area law, not for the vector, is it right?
Yeah. I mean, you're saying that the RT surface is the edge.
It just
Could be. Actually, there is a setup to check it. I mean, discussing it on. I mean, you know, there's a setup where it's possible to check actually. Like, you know, there is a setup. You take ADS3.
yeah.
ADS3. So this is a 2 plus 1, 1 plus 1 dimension. And there's a 2 plus 1. And then you take the RT. Okay. Of course, when you do it in the vacuum, it's C/3 log the length or something. The vacuum and the length is this. Now, but if you do an excitation in the TFT, see it. So it's like, as I said, so we create an operator and then you look at the entanglement length with X. So there will be corrections to it, functional lengths.
Yes.
And that has been evaluated in CFT. Then we look at whether we can reproduce that in the bar. Now, it seems that in that particular case, not only we have to deform the RT surface, you have to also calculate this bulk. Only then it agrees. I think a paper by Bellin and so on.
Calculate the bulk as
S bulk. That S bulk. There are two terms actually. So basically, you have to excite. You have to introduce that excitation which you have created for the O. The dual of that, which is the scalar in the bulk. You have to deform the geometry with that. So the function. It's quite an involved calculation actually, and then calculate both of these things. But you could do descendants of this. D to the n of this. That or descendants of the vacuum. That involves gravitons in the bulk. I'm just saying hypothetical scenario. Gravitons in the bulk. And then the question is whether it's such, I mean, how the detail, whether we can actually isolate. Because the CFT calculation is simple. I mean, we have the result for the CFT. The bulk is quite important in this case.
Is there any other question?
Yeah. Suppose now that you try to make a similar analysis in the context of the black hole instead of, because there is also this notion of entanglement of two different regions. What would this graviton log coefficient?
So that's the problem. I mean, one of the reasons we got into all this is because, you know, there are lots of things, discussions in the literature that we can't define the entanglement. Because, you know, you can't separate a region because if it is nonlinear, if the theory is nonlinear, there is a Gauss law which tells you that, you know, if you know outside, if you know the information outside, you know the information inside. I think there are a lot of discussions recently. So therefore, you cannot separate these. You can't bipartite at all. So that's a higher order question. And for the black hole, we need the G Newton. I don't know how to do it actually. Yeah. I mean, this is very simple. I mean, this thing is very simple. You have to turn that G Newton on, and then I don't know how we can.
in the holographic thing, do we understand how to go between choices of centers and so on?
Not exactly. Yeah, actually, I don't think it's correct. Is there a way to see it? Yeah, to set it up. I don't know actually. Yeah, it's not understood. I don't think people have thought about the centers.
And how do you understand the SO2 part here? Like what?
Oh, this is that, you know, like it splits, it's a plane. It's a two-dimensional plane in 4 dimensions. Yeah. I mean, the entangling surface is a 2-dimensional plane. And the full direction is SO4 for symmetry. It just breaks it. It's like having a plane, 2 planes. One is time and y, and the other one is x and z. X and z is a plane. This is a plane. The second calculation is not for the sphere. It's for a half plane, half space. So here there is t and y and x and z. That's it.
Hi, I had one question. Hello.
Yes, yes.
Justin, can you go back to the slide where you have calculated the after the quench?
Thanks. Yeah.
Actually online. So you have calculated the Rene entropy. So I just wanted to know what is the analogous of n here, like in the standard replica trick. What is the analogous of n in this Wilson loop approach? Like what is this limit?
The n goes to 1 is of course the entanglement. N is actually the defect angle on the cone. Because when you do the replica trick for this particular case, the geometry becomes the conical geometry. It's like cones joining n, and it becomes a cone. So the 2-point functions are all evaluated on a cone. That's actually the replica here. Yeah.
So like in the standard CFT, when we have all these sheets, so this is like we have bunch of cones here, like something like that.
Yeah, the cones. Yeah, so the sheets are joined. You can see the picture.
Cannot see.
Yeah.
I cannot see the blackboard.
Yeah, so like you can join one sheet is there, and then there's a branch cut, right? One sheet is there, and there's a branch cut. Then join another sheet on it, right? On the branch cut, and keep going. And then finally, it's a 2 pi n cone. You can think of that whole thing as a 2 pi n cone. And you know, the geometry has to be taught in that language, and it's similar to the two-dimensional case actually. But you have to look at correlators on that particular surface. In the two-dimensional case, you have conformal symmetry so that you can map it back on the plane.
Yeah, we map it to the complex plane. Yeah.
But here you have to calculate it directly on that surface actually, and those correlators are known, and that's how.
I see. Okay. Yeah, that's the question. Thank you.
If there is no more question, let's thank speaker again.